two isotopes of iodine are 12553I and 13153I. Determine for these two isotopes the difference between the constituents of the nuclei. So the first thing to work out here is what the numbers actually mean on each of these isotopes. So let's look at the top number to begin with. Now the top number represents the number of nucleons, and that's going to come in useful in a later question as well. So the number of nucleons, and that's the number of protons and neutrons. The number on the bottom is just the proton number, and that determines which element that we're dealing with. So that I, the iodine, anything that's iodine will always have 53 protons. Now you'll notice that to find the number of neutrons in an isotope, we subtract the bottom number from the top number. What you'll notice with this is where the nucleon number of iodine 125 is lower by 6 than iodine 131, iodine 131 will have 6 more neutrons. And to get that mark, you need to be specific by saying that there are 6 and that it's neutrons. You can't say 6 more nucleons, for example. An iodine 131 nuclide undergoes beta decay to form a xenon nuclide. State the nucleon number of the xenon nuclide. Now with beta decay, the nucleon number does not change because either a proton turns into a neutron or a neutron turns into a proton. And remember, where protons and neutrons are both nucleons, that overall number doesn't change. So actually it stays at 131. You don't need to explain why for that question, it's just one mark. You just need to state the value. An iodine 125 nuclide decays by electron capture to form a tellurium nuclide. State two differences between the constituents of the iodine nucleus and the tellurium nucleus it decays into. So let's first of all work out what's happening with electron capture in this nuclide. So with electron capture, what typically happens is a proton absorbs an electron. You could say that it captures the electron and it sort of turns into a neutron. So what you've got there is a balancing of charge where you're combining a positive proton with a negative electron to form a neutral neutron. So let's write that down. So in that overall process, what's actually happening is by absorbing an electron, we're losing a proton and we're gaining a neutron. So the two things that we can say are, first of all, that the tellurium nuclide has one more neutron than the iodine nuclide. Second thing that you can say is where during that process the iodine 125 nuclide has lost a proton, the tellurium nuclide has one fewer proton. And then your 2 marks are going to be for making those 2 points that I've written in black. Internal conversion is a process in which a nucleus in an excited state can release its excess energy. In internal conversion, all of the excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force. This orbital electron is ejected from the atom. The tellurium nucleus formed in the previous question is in an excited state and can undergo internal conversion. Discuss 3 differences between internal conversion and beta minus decay. Now what I'm going to do for this question is I'm going to write down the 3 answers that you could have. I'm going to write a few more and just talk about those and explain why there's differences between the 2. So the first thing to say is actually quite a useful similarity. If it was asking for similarities, would be that in both cases, an electron, a negative electron, is released. Remember that the orbital electron in internal conversion is ejected from the atom, but unfortunately we're looking for differences, so we can't say that. The first thing I would say actually is that where internal conversion is all about the energy from an excited state, there's no actual change to the structure of the nucleus throughout that whole process. Whereas in beta decay, we've got this idea that a neutron turns into a proton and therefore an electron is released. So let's write that down first. So yeah, beta minus decay. If it's beta minus decay, we've got a neutron turning into a proton, And if it's beta plus decay, we've got a proton turning into a neutron. So leaning more into the idea of energy, we could talk about what values those energies could take in this process. Now, bear in mind that in internal conversion, we're dealing with electrons in orbitals, in shells around the atom, and they take very specific values. They're very discrete. So when we eject electrons from the atom, they will have discrete energy values also. Whereas in beta decay, there could be a continuous range of energies that could occur. You could say the same for momentum as well. Now, for a third mark, we could also talk about what else is released in beta decay that wouldn't be released in internal conversion. So let's first of all write down the equation for this beta decay, or at least the general equation. No, I should say here, obviously I've said beta, but I mean beta minus. One thing that we've missed here is the neutrino that's also released to balance the lepton number, because we're releasing a lepton, this electron, at the same time. So actually there's an anti-neutrino released, which doesn't occur in internal conversion. So just a couple more points to add, because there are two more that we could include here. Now, a fairly obvious one, with internal conversion, we're dealing with electrons in shells, whereas in beta decay, we're dealing with the nucleus. So we should have said that at the start, really, but actually it's an important point to make. And then finally, you could talk about the forces involved. Remember in the question, it mentions the electromagnetic force. There are other forces that we can use, namely the weak interaction, or the W boson, the W minus boson, which relates to the beta decay, but that doesn't take place in internal conversion at all. So let's write down that difference as well. And those are the 5 points that you could have. It should be fairly obvious, but it's 1 mark per point. If you miss any of those, or if you only get 2, then you only get 2 marks. You get the idea. Maximum of 3 there. Some cars are fitted with a water sensor designed to switch on windscreen wipers automatically when it rains. Figure 1 shows a simplified diagram of the sensor. And then we've got figure 1 here, where you can see there's a panel of glass. There are 2 prisms underneath with LEDs shining through, and then we've got that total internal reflection that's occurring at 45 degrees. A light ray travels from the light-emitting diode, the LED, through the first prism and into the windscreen. The ray reflects off the surfaces of the windscreen at A, B, and C, and then passes through the second prism into the detector. Suggest how the design ensures that there is no deviation of the ray as it enters the first prism. Now, what you'll notice with this diagram is that as the light comes in from the LED, it's entering at a normal to the surface, and that's the only angle of entry of that light at which there is no distortion, there's no bending. If the light were to come in at a different angle, for example, this way, you would expect it to bend towards the normal. So actually, it would probably come out something like this. So the design is such that there is no deviation of the ray because the LED is entering the glass at a normal to the surface. Suggest 2 features of the design that ensure there is no deviation of the ray as it leaves the first prism and enters the windscreen glass. So you'll see on this diagram, they're referring to this area where the light continues to travel in a straight line. Now, in order for that to happen, we need to ensure that there is no refraction between the first prism and the windscreen. And the only way that we can guarantee that is if those 2 materials are the same, so they have the same refractive index. If we write down Snell's law underneath, between material 1 and material 2, you'll notice that if we keep the values of n the same, then that means that the values of theta have to be the same as well. So that's why it's important to have that same material. The second point to make is that there can't be any gaps in between the prism and the windscreen glass. If there were, then you'd have sort of air bubbles. And remember, air has a different refractive index to the glass that these parts are made of. So that would cause a distortion of the light. So there would be a refractive effect and possibly even total internal reflection if the light was trying to escape the glass into the air. So 2 marks up for grabs there, 1 for each point. If you miss one, you miss a mark. The refractive index of the windscreen glass is 1.52. Explain why the ray follows the path shown inside the windscreen glass in figure 1. Support your answer with a suitable calculation. Now, the equation that we want here is the equation relating critical angle to refractive index. So if we substitute our values into a rearranged version of this equation, so we end up with a critical angle for this boundary of 41.1 degrees. So what that then means is, as long as the angle is within 41.1 degrees, then there will be some refraction. Or alternately, if the angle of incidence is larger than the critical angle, then there will be total internal reflection. Now, because that light is hitting the boundary at 45 degrees, that's larger than the critical angle, so there will be total internal reflection. So for this question, you get 1 mark for correctly doing the calculation and working out that the critical angle is 41.1 degrees. And then you get another mark for explaining why that value is significant and how there's only total internal reflection occurring. When it starts to rain, water droplets form on the outside of the windscreen as shown in figure 2. So we've now got these water droplets that have appeared. And we're interested in the refraction or maybe reflection effects that occur when those are there. The refractive index of water is 1.33. Explain why the presence of water at A causes the intensity of the light at the detector to decrease. Support your answer with a suitable calculation. The first thing that we want to do here is calculate the critical angle at this glass water boundary. Now, it's not going to be as simple as using that previous equation that n equals 1 divided by sine of c, because we have 2 different values of n that we need to deal with. Now, that original n equals 1 divided by sine c comes from the assumption that the refractive index of the material that you're going into is near to 1, i.e. is practically a vacuum, and that equation kind of holds up for something like air. But because we're dealing with water now, we need to use 1.33. So we need to start from first principles. Let's write down Snell's law one more time. And let's think about how we can modify this to put our values in. So if we make anything with a 1, the glass, and we make anything with a 2, the water, let's substitute our values in first. Now, the reason I've put 90 degrees here is because that's the angle at which there's no longer just total internal reflection. It's the angle at which the light will start to refract out of the boundary and travel along the surface. I just draw that up here. So it's now moving along from right to left rather than reflecting in. And as you can see, that's at 90 degrees to the normal. So if we rearrange this equation to find out what the critical angle for that boundary is, now this is where we can simplify this, because we can say that sine of 90 degrees is equal to 1 anyway. And we should end up with 61 degrees. So that's our first mark for making that calculation. The second mark would be for saying that actually now the critical angle is much larger than the angle of incidence. So it's not just total internal reflection that's taking place now. And then there's your second mark for making that point. So 2 marks. The refractive index of the windscreen glass can vary by a few percent across the thickness of the glass. Discuss how this variation may affect the path of the ray through the windscreen glass. The first thing that we want to say is, based on the calculations that we discussed just now, refractive index is everything here because it affects how light can bend. Anytime there's a variation in refractive index, there will be a distortion of the lights. So let's write that down first of all. Now, I've included there or at normal to a boundary, because that's also a situation where it could carry on traveling through in a straight line, just like we saw at the very start of this question. The second point to make would be that actually where the refractive index of the windscreen glass is only varying by a few percent, it's unlikely to affect the path of the beam that much. So it won't be enough of a change to cause this mechanism not to work. So you notice we've got 2 points there. It's a 2-mark question, 1 point, 1 mark for each. A different design has the LED and the detector further apart. The ray undergoes more reflections inside the windscreen glass before reaching the detector. Discuss 2 ways in which this different design affects the sensitivity of the sensor to the presence of water droplets. Now, there are 2 ways we could go with this question. We could say that it becomes more sensitive. We could say that it becomes less sensitive. There are arguments for both. We're going to explore both of those now. So let's look at this mechanism becoming more sensitive first of all. Now, if the light is bouncing off the glass boundary more often, then there's more chance of it bumping into some water droplets. Bit of a crudely drawn diagram there, but you can kind of see that every time the light ray hits the upper surface, if there's a drop of water there, then there's going to be a refraction effect. Now, if there are fewer of those zigzags, then there's less of a chance that the ray will travel through water. So that's the first point to make. Now, the second thing to say is that where the light is traveling further, its intensity will be much lower when it reaches the sensor. So the sensitivity to rain will be much higher in that case. Now you can see there that when there is rain, there's going to be a particular drop in intensity due to refraction effects. And if that light intensity is lower in the first place, then it's going to be a more significant change in comparison to the original intensity than if you had a really bright light in the first place. Now let's have a look at the less sensitive side. Now, whilst it's true that light is more likely to reach a water drop on its path from the LED to the sensor, it could also reach other forms of debris such as dirt or dust, and those could cause disruption of the light signal. You could also make reference to any scratches in the glass that could cause the light to be distorted in a particular way. It's more likely that you'll reach one of those as well. You could also mention how the windscreen absorbs more of the light, so there's actually a reduced intensity when the water is not there. You could also mention the curvature of the glass, so this curving effect will mean that the light might not actually reach the detector in the first place. So whether you discuss the idea of it becoming more sensitive, whether you discuss the idea of becoming less sensitive, is 1 mark per point. And even if you had 1 from each, you could still get those 2 marks. If you're discussing it, then you could be talking about both sides of this story. So 1 mark for each of those points, but a maximum of 2. Figure 3 shows an arrangement to investigate diffraction. White light is incident on a single slit. After leaving the slit, the diffracted light passes through a green filter to reach the screen. And then we've got a single slit there in the diagram with the green filter and the screen. Describe the pattern produced on the screen. So we want to talk about the interference pattern that's been produced by this. You might be wondering, well, how does a single slit actually produce an interference pattern? Surely it's just double slits and diffraction gratings and so on. The thing that I would use to answer this is Huygens principle. So according to this principle, a wavefront can be considered as a line of point sources. So in this gap here, in this slit, what's actually happening is you have the wavefronts that travel through the gap from the white light source, and then each point on that wavefront is its own point source, and they then expand outwards, and you can think of it as being a diffraction grating with an infinite number of slits. So we get this pattern that's produced on the screen. The first thing to say is that there's going to be a maximum at the center, just like what you would have if you used light with a diffraction grating. Now that deals with the intensity of the maxima, but let's also talk about the width of the central maximum compared to the maxima on the sides. So those are your 2 marks there, one for each point. The green filter is replaced with a red filter. Describe the change in the pattern produced on the screen. Now for this question, I would refer to the diffraction grating equation. And what that will do is it will tell us how the pattern size, how the spacings of the maxima will be affected by the wavelength. So let's write that down. So red light actually has a longer wavelength than green light. So what that actually tells us is that a larger wavelength will give us a larger value of sine theta because we're keeping n and d the same. So the maxima will be further apart, and that's our first mark. The second point to make is about that central maximum. It's actually going to be wider in the same way that the maxima become further apart. You're actually stretching the maximum itself in the middle. And then that's your second mark. A diffraction grating is placed between the red filter and the screen. The diffraction grating has 500 lines per millimeter. Light is incident normally on the grating. Figure 4 shows the arrangement. So this time we've got that single slit, then the red filter, then the diffraction grating, and you can see that pattern produced on the screen. The wavelength of the red light is 650 nanometers. Calculate the angle theta between a first order maximum and the central maximum. So for this question, we just want to use that diffraction grating equation again. Now, before we make any substitutions, we're going to need to substitute a value for d, because we're not given d, we're given the number of lines per millimeter, which is 500. So let's convert that first of all by first working out the number of millimeters per line and then the number of meters per line. So I've made a quick conversion there. You'll notice that either side of the word per, we've got lines per millimeter and then millimeters per line. You just need to invert the value. So do 1 divided by that value. So 1/500 millimeters per line. And then to convert from millimeters to meters, we need to divide by 1,000 or multiply by 10 to the power of -3. So that's going to give us a value of 2 times 10 to the power of -6 meters per line, which is also the slit spacing. Now let's rearrange that equation to make theta the subject and then substitute in our values. So just bear in mind there that the value of n is going to be 1 because it's the first order maximum, and that we've converted our wavelength into meters, so 6.5 times 10 to the -7 meters rather than 650 nanometers. Remember, we want to work in SI units, and that gives us 19 degrees. So in terms of marks, it's very straightforward. You get a mark for calculating the slit spacing correctly, and another mark for correctly calculating the number of degrees. So an example of where you might get 1 mark, you might incorrectly calculate the slit spacing and substitute it in wrongly, but still do the correct calculation using n lambda equals d sine theta. So you wouldn't be fully wrong, but you'd only get 1 mark. In practice, the filter transmits red light with wavelengths in the range 600 nanometers to 700 nanometers. Suggest how this affects the appearance of the maxima. Now, if we've got a range of wavelengths here rather than specifically 650 nanometers, we're going to get our pattern is going to become a bit more fuzzy, a bit broader. We won't have defined maxima like we would have done with just 650 nanometers. So let's write that down first of all. What you could also say is that for the greater order maxima, you would get broader, more spread out maxima, because remember, lambda is not proportional to theta. There's no direct proportional relationship between that wavelength and that angle. So the angles at greater values of n will be more affected. Now, what you could also mention is that for the third order maximum, at longer wavelengths, i.e. 700 nanometers, that angle of theta is going to go above 90 degrees. So if you put that calculation into your calculator with a value of n being 3 and a value of lambda being 7 times 10 to the -7, you would actually get what's called a math error on the calculator because it doesn't know how to work that out. You can see that it's a top-heavy fraction, and you can't put a top-heavy fraction into a sine to the power of -1. So what that tells us is that the third order maximum at longer wavelengths would be cut off. So these are all valid points, 1 mark each. The last thing that you could say is also that the central maximum would not change width. So 2 marks there, but a mark for any of those points. Figure 5 shows a simplified catapult used to hurl projectiles a long way. We've got a diagram here. You can see there's a wooden beam that goes right the way through the middle, and it's balanced on one side by a counterweight up here, but then there's also on the other side a sling and a rope which are providing a force to balance that out. And we're going to look at the idea of how the moments contribute towards each other very soon. The counterweight is a wooden box full of stones attached to one end of the beam. The projectile, usually a large rock, is in a sling hanging vertically from the other end of the beam. The weight of the sling is negligible. The beam is held horizontal by a rope attached to the frame. The catapult is designed so that the weight of the beam and the weight of the empty wooden box have no effect on the tension in the rope. Suggest how the pivot's position achieves this. So the pivot here is at the center, and we're interested in the forces acting on one side and the forces acting on the other. Now, just dealing with the beam and the counterweight for now, the way to cause this to balance, ignoring the rope and the sling, is for the center of mass to be at the pivots. Now, that's the center of mass of the beam and the counterweight put together as one object. Now, in addition to that, to get the second mark, you're also going to need to talk about how the moments balance. So you could say that the net moment is 0. You could say that the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. I think for this, it's fine to say that the net moment around that pivot is going to be 0. So remembering there that the center of mass is the point at which all of the mass is concentrated. So it's the point around which all moments are balanced. So those are your 2 marks. The stones in the counterweights have a total mass of 610 kilograms and the projectile weighs 250 newtons. Calculate the tension in the rope. Now, this is a 5-mark question, so we're going to need to look really carefully at how we can achieve all of those marks. Let's go back to the diagram first of all. So to begin with, it's worth considering what's contributing to the clockwise moment and what's contributing to the anti-clockwise moment. Remember, the weight of the beam and the weight of the box are irrelevant because when there's no load added, the beam is in equilibrium. So only the projectile or the rock and the stones in the box are contributing to this, to these moments. Also the rope, I guess. So contributing to the anti-clockwise moment, we've got the weight of the projectile, which will just act vertically downwards, and the vertical component of the tension in the rope. Remember, the horizontal component of that tension is going to be acting towards the pivots, so it's not going to be a perpendicular force to that beam itself, so there's no moment from that. Now, in terms of the clockwise moment, so for this, it's just the weight of the stones, and that weight is acting vertically downwards as well. So we're treating this system as being in equilibrium, so we can say that the clockwise moment is equal to the anti-clockwise moment. And on that basis, it's worth just filling in what contributes to each of those. So just to clarify what I mean here, we've got the weight of the stones multiplied by the distance of the stones from the pivots is equal to the weight of the projectile added to the vertical component of the tension. All of that is then multiplied by the length of the arm. Now you'll notice that the 2 forces in the anti-clockwise moment both act at the same point, so we can add both of those moments together and factorize so they're both multiplied by the length of the arm. So let's now substitute in our values. So you'll notice that the only unknown there is the tension, which is what we're trying to find. So then the rest of the marks will be achieved by calculating that value of tension by rearranging. So let's do that. So first step of the rearrangement, we divided both sides by 4. We've then subtracted 250 newtons from both sides. And then the last thing to do is to divide both sides by a sine of 50. Now, if we put all of that into a calculator, we should end up with 2,600 newtons, and that's the value that we're going to put into the answer box. So the actual answer there is 2,603 newtons, but we've rounded this to two significant figures because the values that were given in the question are two significant figures, so that's what we have to stick to. Now, in terms of number of marks, we get a mark for calculating the clockwise moment and a mark for calculating the anti-clockwise moment. We get a mark for saying that the clockwise moment is equal to the anti-clockwise moment, a condition of it being in equilibrium. We get a mark for mentioning that it's t sine 50 and not just the value of t, so correctly calculating the vertical component of the tension. And then finally a mark for getting 2,600 newtons. Now, it's possible to miss some of these marks and get an answer at the end. It won't be the correct answer, but it will mean that you won't lose all of the marks. So it's worth just knowing step by step where those marks come from. When the rope is cut, the counterweight rotates clockwise. When the beam is vertical, it is prevented from rotating further. Projectile is then released horizontally with a velocity of 18 meters per second, as shown in figure 6. The projectile is released at a height of 7.5 meters above ground level. And then we've got a diagram that's basically showing that. So you can see that kind of parabolic path of the projectile. The range of the catapult is the horizontal distance between the point where the projectile is released to the point where it lands. Calculate the range and ignore air resistance. And it's a good thing that we are ignoring air resistance because that would complicate the calculations quite a bit. So this range here is what we want to calculate. Now, the first thing that we want to do is use a vertical Subad equation to work out the time taken for the projectile to fall vertically to the ground. Because once we've worked out that time, that's also the time taken for it to travel horizontally across that range. And if we know that its horizontal velocity initially is 18 meters per second, it's going to be the same when it reaches the other end. Remember, the horizontal component of the velocity is not changed because there's no horizontal forces acting on that projectile. So by that endpoint, we can just use speed equals distance divided by time. So vertical time, first of all, I'm choosing to use s equals ut plus half at squared because we can simplify this equation. But because the initial velocity vertically is going to be 0, we can say that u is equal to 0, and therefore s equals half at squared. So we're interested in the time taken, so let's rearrange to make t the subject. So the time taken is going to be equal to the square root of 2 times the displacement divided by the acceleration. So let's put the values in, remembering that a is just the acceleration due to gravity, which is 9.81 meters per second squared. That should give us a value of 1.2 seconds. What we can then do is use that time to calculate the range, because remember I said before that the horizontal velocity is unchanged, so we can use an equation for constant speed rather than a Suvat. So speed equals distance divided by time, aka distance is equal to speed times time. So your answer should be 22 meters. So your first mark will be for correctly rearranging and substituting to find the time. And then your second mark will be for correctly calculating the range. Just to add in a quick note there about the horizontal component and the vertical component, just to avoid any confusion. In another release, the sling is adjusted so that a projectile of the same mass is released just before the wooden beam is vertical. The projectile is not released horizontally. Discuss the effect this change has on the range of the catapult. Now, there are two possible effects on the range, and the only two ways that this can go are it's going to increase the range or decrease it. So let's discuss both of these ideas and see whether marks can be obtained in each argument. So if you picture this catapult, let's just go back to our diagram a second. Here, the arm or the beam is vertical when that projectile was released, but in our theoretical example, it's further back. You have to excuse my diagram there, and you can see that it's being released with now a vertical component of its velocity. Now, I'm not going to write 18 meters per second on that arrow just yet because it may not be exactly that value, but we'll discuss that shortly. What we therefore have is a longer time taken for the projectile to travel because it's traveling upwards and then down. That initial calculation we did at the start of the previous part of the question, where we calculated the time of flight, that time is now going to be longer because it takes longer to travel up and back down again. And over that time, in theory, it should then travel further. So let's write that down in the increase column. Vertical component of velocity is non-zero. So what I mean there is it's got an upwards vertical component of its velocity. Time of flight is greater, so it takes longer to travel. Therefore, it has a larger range. So that could easily be 3 marks right there. So for the decrease arguments, let's look back at our diagram. Now, although we do have a vertical component of that velocity, the box of counterweights hasn't moved as far, so it's not had as much of a chance to accelerate this projectile. So actually, the projectile has less kinetic energy when it leaves the catapult. So the first point to make is that the counterweight doesn't fall as far. And therefore, it doesn't lose as much gravitational potential energy, which it's then converting into kinetic energy of the rock. So what that will then mean is that the rock has a lower initial speed. Because of this equation, kinetic energy is equal to 1/2 times mass times the speed squared, and therefore it's going to have a lower range. Now, interestingly here, I've got 4 points, each of which is mark worthy. But what you need here is, for either side, a combination of 2 points of reasoning and 1 piece of conclusion. So where it says therefore larger range or therefore lower range, that's your conclusion. You need that mark and 2 of the earlier marks to gain all 3 marks. You can also include the argument that there's an increase and a decrease, and therefore the range is unchanged, or it's difficult to determine the range because you've got 2 contradictory changes, and that would get you 3 marks as well. But you would need to conclude that either the range is unchanged or you have an indeterminate answer. So 3 marks there. Safety barriers are used on UK motorways to prevent vehicles crossing from one carriageway to the other carriageway. The barriers also absorb some of the kinetic energy of a vehicle and deflect vehicles along the barrier. The standard test of a safety barrier uses a vehicle that contains dummies. The total mass of the vehicle and its contents is 1.5 times 10 to the 3 kilograms, and its initial speed is 110 kilometers per hour. Show that the initial kinetic energy of the test vehicle is 700 kilojoules. So it's quite useful here that we've got a show that question, because we'll be able to tell if our answer is correct. And there's one typical pitfall in a question like this that will lead you to the wrong answer and therefore encourage you to go back and check and make changes. So the first thing to be aware of is this 110 kilometers per hour, which we need to convert to meters per second before converting into joules. So 110 kilometers per hour, let's first of all convert that to meters per hour and see what we end up with. So we've got 110,000 meters per hour. Remember, there are 110,000 meters in 110 kilometers. So if you're traveling 110 kilometers every hour, you're traveling 110,000 meters every hour. We next need to convert into meters per second. So we're going from hours to seconds, the conversion factor being 3,600. There are 3,600 seconds in an hour. So we're dividing by 3,600 here, because if you're traveling 110,000 meters every hour, every second is going to be a 3,600th of that amount of time. So you're only going to cover that fraction of distance. So we should end up with 31 meters per second. It's 30.5 recurring, but we're going to round it. So this is a speed value that we can then put into our kinetic energy calculation. So let's write down the kinetic energy equation first of all. So kinetic energy is equal to 1/2 times mass times speed squared. So let's substitute in our values. Don't forget to square the 31, and we should end up with 7.2 times 10 to the power of 5 joules, which is approximately equal to 700 kilojoules. Remember, a kilojoule is 1,000 joules. So for this question, you'd get your first mark for correctly converting 110 kilometers per hour to 31 meters per second, and then your second mark, not for getting the 700 kilojoules at the end, but for correctly substituting that value of 31 meters per second into the equation. Because the rest of that question is just assuming that you can put numbers into a calculator, which most people can do. So those are your 2 marks. The test vehicle hits a steel safety barrier at an angle of 20 degrees as shown in figure 7. You've got figure 7 there. As described, the car is travelling towards that safety barrier at 20 degrees to its surface. Calculate the component of the momentum of the test vehicle in a direction along the line of the safety barrier. Give an appropriate unit for your answer. Well, the first thing to say is the unit is going to be kilogram meters per second, because it's momentum that we're dealing with. So even if you don't know anything about how to calculate this question, it's a nice easy mark there by saying kilogram meters per second. Always worth writing that down early on, just in case, I don't know, run out of time or something like that. So in terms of the car approaching the barrier, it's approaching at 20 degrees. We want to know the components in the direction along the line of the safety barrier. So let's draw a triangle. So we've got our right angled triangle there, and we're interested in the horizontal line, and that's going to be our answer. So we've got the momentum of the car coming along, because momentum is equal to mass times velocity. It's important that we use velocity here and not speed, because velocity is a vector quantity, as is momentum, because we're dealing with directions here. Now we've got the angle, we've got the adjacent side to that angle, and we've got the hypotenuse. So if we use SOHCAHTOA, so we're interested in the part of the expression that has the adjacent and the hypotenuse. So that's going to be this middle part. So cos of the angle is equal to A divided by H, the adjacent divided by the hypotenuse. So let's make those substitutions and then rearrange to make P the subject. And that should give us 4.4 times 10 to the 4 kilogram meters per second. So in terms of marks, we first need to indicate that we've used the momentum equation. So you might want to write P equals mv down in this answer space, but we have actually multiplied the correct values together, and the examiner should realise that. We've got a mark for getting the correct value, and then a mark for getting the correct unit. So 3 marks there. Immediately after the collision, the test vehicle moves along the safety barrier with no change in its momentum in this direction. Show that the kinetic energy lost in the collision is about 80 kilojoules. So the initial kinetic energy is going to be 700 kilojoules. Now we want to use the momentum to calculate the final kinetic energy. So that's equal to the mass times the velocity. Now the velocity is what we're interested in, because the magnitude of that is going to be the speed that we use. Now we can also say, with this calculation, to find that velocity, we could just do 31 times cos of 20, because we can just find the component of the velocity in that direction. That's a perfectly valid way of doing it. So we end up with 28.7 meters per second. Now let's put that back into the kinetic energy equation. And we end up with 618,000 joules. Now that answer is rounded from 617,767.5. But as long as you're showing that it's about 80 kilojoules difference, then it shouldn't matter. So we end up with a difference of about 82,000 joules, which we can then round to 80 kilojoules. So for this question, you'll get a mark for correctly calculating the velocity in the direction of the barrier. You'll get a mark for calculating the final kinetic energy, and then you'll get a mark for correctly subtracting the final kinetic energy from the initial kinetic energy to find the change. So 3 marks there. The steel safety barrier deforms during the collision. For the barrier to pass the test vehicle should not move more than 1.5 meters towards the other carriageway. The barrier can apply an average force of 60 kilonewtons at right angles to the carriageway. Deduce whether the safety barrier will pass the test. Now, the first thing that I would write down for a question like this is the work done equation, which is work done is equal to force times distance. But the thing to note here is it's force times distance moved in the direction of the force. So let's write that down as well. And you'll notice that actually those are aligned anyway. It's 1.5 meters towards the other carriageway, so it's in the direction that's perpendicular to the barrier, and the force is at right angles to the carriageway anyway, so that's in the same direction. Now, if we rearrange this work done equation to find what that force would be, so we've divided 82,000 by 1.5, so that's the 82 kilojoules that we dealt with in a previous part of the question, and we're dividing that by the 1.5 meters that barrier can be deformed by. So that gives us 5.5 times 10 to the 4 newtons. Now we can say that that's less than 60 kilonewtons, so the barrier will pass the test. Now, in terms of where the marks are awarded here, we'll get a mark for correctly rearranging the work done equation. We'll get a mark for correctly calculating the value of the force, and then another mark which summarizes the reasoning and making that conclusion at the end. Now, there are other ways of doing this question. You could do the question in terms of impulse or Newton's second law using F equals ma. You can use Subat equations, but actually this is the quickest, most straightforward, easiest way to do this question, so that's what I would stick with. So 3 marks there. A different safety barrier uses a solid concrete wall which does not deform. The same standard test is carried out on a concrete wall. Discuss which type of barrier would cause less damage to the dummies in the test. The key part to note here is that the concrete wall does not deform. Now what that means is on that concrete wall, the car is going to be in contact with the wall for less time. Now in terms of impulse, which is equal to force times time, if that amount of time is shorter, and that means for the same impulse, because the same change in momentum, we're going to get a larger force. So actually the concrete wall would be worse. So therefore the steel barrier is better. Now you could also answer this question in terms of stopping distance, because you're increasing the stopping distance using a steel barrier rather than a concrete wall. So in terms of work done, what you've got there is for a constant work done, if you're increasing the stopping distance, you're going to have a smaller force, or vice versa. So in that respect, the steel is still better. So your 2 marks would be for making those 2 points. A loudspeaker cone is driven by a signal generator or an oscillator. Figure 8 shows the variation of displacement with time t for a point P at the center of the cone. P is oscillating with simple harmonic motion. And that's an important point there because that comes with a load of definitions and equations that we can use later on. So figure 8, we've got our graph, sinusoidal, or technically it's a cosine graph because it starts at a maximum point, but it's a displacement time graph. So we're probably going to need to analyze that. State the time in milliseconds when P is moving at its maximum positive velocity. Now remember, velocity on a displacement time graph is the gradient. So let's write that down first of all. So velocity is the gradient of the graph. And remember that where displacement is a vector, velocity is also a vector. So we need to take into account that that velocity could be negative as well. So the only points on this graph where there is a positive velocity is between 1 second and 2 seconds. The region between those 2 points is the only region where this curve is traveling upwards. And the steepest point is going to be at 1.5 milliseconds. So this is where the gradient is going to be the most positive, and this is where the velocity is going to be the highest. So we only need to state in this question. We don't need to provide an explanation or an analysis of the graph, so nice easy mark there. Calculate the maximum acceleration of P. Let's go back to our graph. Now, in order to calculate the maximum acceleration, we need to use the maximum displacement because the equation that we're going to use, and we'll write this in the answer space, A is equal to minus omega squared x. Now let's just write down what each of those things mean. Now we can modify this equation slightly to include just the normal frequency, so we don't have to calculate the angular frequency, but also to include the amplitude. So what I've done there is I've made a substitution, omega equals 2 pi f. So the angular frequency is equal to 2 pi times the ordinary frequency. And then I've included the amplitude because the maximum acceleration occurs at the most extreme points in its motion, i.e. when the displacement is equal to the amplitude. So we need to go back to our graph and we need to recover some values of f and of capital A. Now we can use the time period of this oscillation to find the frequency, first of all. So the inverse of the time period is the frequency, and you'll notice that the time period, let's go from 0.5 to 2.5, is going to be 2 milliseconds. Make sure you say milliseconds and not seconds because you could lose a mark. I've done 1 divided by 2 times 10 to the power of minus 3 to get an answer in hertz, because the time period needs to be in seconds for the frequency to be in hertz, because that's SI units. So we end up with 500 hertz. So that's our frequency to start with. Then we need to find the amplitude, which is just the maximum displacement. You'll notice that this most extreme point up at the top is at 4.2. Let's just look at the units there. So that's in millimeters. So we need to convert that to meters. So 4.2 times 10 to the power of minus 3 meters. Let's just write our two values down in the answer space. So 4.2 times 10 to the power of minus 3 meters for the amplitude, and a frequency of 500 hertz. And it's always just worth writing down where you got that frequency from. So substituting those values in. So that gives us 4.15 times 10 to the 4 meters per second squared. Now, because the full answer is 41,452, if we're going to give that answer to two significant figures, it's going to need to be 41,000, which is 4.1 times 10 to the 4 meters per second squared. Now that's a lot of work that we've done for 3 marks, so let's just identify where those marks are obtained. You get 1 mark for correctly identifying the time period, so it's always useful to write that down. You get another mark for correctly identifying the amplitude, and then your last mark will be for getting the answer correctly at the end. Obviously, if you've done all of your calculations correctly with the values that you've obtained from the graph, then that shouldn't be a problem. The loudspeaker creates variations in pressure and produces a sound wave in the air around it. State the type of wave produced and describe the motion of the particles in this type of wave. This is only 1 mark, so really you just need to write down the type of wave and how that wave can be defined. So this is going to be a longitudinal wave. Now there are only 2 types of wave that we could have included here, the other one being transverse. Now a longitudinal wave is going to be where the particles are oscillating parallel to the direction of motion, which is what we're going to write down in a second. But in a sound wave, that's how the air molecules vibrate. They vibrate back and forth if the wave is traveling forward, but we need to define it relative to the direction of the wave. So only 1 mark here. It's a little bit harsh, but that's really all you get for writing a term and its definition. You must say parallel, and you must say either energy transfer or direction of travel, because the energy is transferred in the direction of the wave. And you must correctly say longitudinal and not transverse. 1 mark. Figure 9 shows a practical circuit in which a variable resistor is used to control the brightness of a lamp. The voltmeter reading is monitored as the variable resistor is adjusted to make the lamp brighter. Now, you've got your diagram of the circuit there. The thing to note, which I've just highlighted, is that it's a practical circuit. So these components are going to be realistic. They don't obey any kind of idealistic scenarios. So it's the cell that we're interested in, which we'll talk about in a second. Explain why the reading on the voltmeter decreases as the brightness of the lamp increases. Now, the thing to note here is that if this lamp is getting brighter, there's going to be a larger current moving through the circuit. And what that means is there will also be a larger current moving through the cell. Now, you notice earlier I said that it's a practical circuit, so actually this cell is going to have some internal resistance. So if we just redraw this cell as it should be, so the dotted line there represents the outline of the cell, and then you can see I've drawn a very small internal resistance there. Now, if the current is larger through that bulb, then it's also going to be larger through the cell and also larger through its own internal resistance. Now, according to the equation form of Ohm's law, if the current going through that internal resistance is larger, then it's going to have a greater potential difference. And what that means is that it's taking away from the EMF of the cell. So actually that voltmeter reading is going to go down because whatever volts the EMF is providing are going to be taken away by the internal resistance. So let's write that down. So if the lamp is brighter, the current is higher. The second mark is going to be for talking about a higher current through that internal resistance, which then reduces the PD. So I said there that the potential difference across the internal resistance is greater, so the overall potential difference across the cell, which is going to be the EMF, subtract the potential difference, EMF being the electromotive force, is going to be lower. Now you can see that voltmeter there is not only across the variable resistor and the bulb, but it's also across the cell. So that will be lower in turn. So the marks here will be for the 2 points that I just made there. The variable resistor is adjusted so that the lamp is at its brightest. The reading V1 on the voltmeter is noted. A second identical cell is then connected in parallel with the cell in figure 9. The new reading V2 on the voltmeter is noted. Explain why V2 is greater than V1. Now, I would annotate the diagram in figure 9, but it's going to get a little bit messy. So what I'll do is I'll draw a separate diagram in this answer space just to explain the effect of adding another cell in parallel. Now you can see there I've drawn two practical cells, each with an EMF and an internal resistance. And as you can see, those resistances are going to be in parallel with each other as well. And what we know about resistance when we put resistors in parallel is that actually the overall resistance is reduced, and it's going to be lower than just one of those resistances. So when two practical cells are placed in parallel, we have the same EMF produced as if there were one cell on its own, but the internal resistance is going to be halved because those two internal resistances are in parallel. So that's going to be our first mark. So just as I said there, we're keeping the overall EMF the same as if there were one cell, but the internal resistance halves because it's a parallel system. Now the second point to make is that according to that equation that I wrote down just now, V equals I times R, if we're reducing the overall internal resistance, then actually the number of volts lost across that internal resistance is going to be lower. So the overall PD across this system of cells, which is going to be the difference between the EMFs and the PDs, is going to be greater. So the overall voltage output of that cell is going to be greater, which when you place a voltmeter across it, there's going to be a larger reading. So just as I said there are fewer lost volts across that internal resistance because it's a parallel system. Now, 2 marks up for grabs here. I've made 2 points, 1 for each. Nice and easy. The process of beta plus decay can be represented by this diagram. Which row identifies particles X and Y? Now what we've got here are, for particle X could be a W plus boson or a W minus boson, and for particle Y it could be an electron neutrino or an electron antineutrino. So let's have a look at the diagram again. Now for this diagram, it's best to consider a conservation of charge. We know that a proton is going to be positive and a neutron is going to be neutral. So in turning a proton into a neutron, we're going to have to lose some positive charge. So this particle X is going to need to be positive because that charge needs to go somewhere. So that automatically narrows this question down. So we know that particle X has to be positive. Now we've got A and B feature W plus bosons, but C and D are W minus bosons. So the answer cannot be C or D. So we're left with A or B, so it's either an electron neutrino or electron antineutrino. Let's have a look at the diagram again. Now, when this W plus boson, as we now know it to be, decays, we end up with a positron and something else. Now, what we need to consider here is that the lepton number needs to be conserved. A positron has a lepton number of -1. So the particle that we produce needs to have a lepton number of +1. Now, if you want to ignore lepton numbers, another way to look at it is that we're producing matter and antimatter from this boson. So a positron is antimatter, so the particle we produce as particle Y needs to be matter. So it would need to be an electron neutrino rather than an electron antineutrino. So the answer can only be A. An electron collides with an isolated atom and raises an orbiting electron to a higher energy level. Which statement is correct? The colliding electron is captured by the nucleus of the atom. A photon is emitted when the electron rises to the higher energy level. An electron is emitted when the excited electron returns to the ground state. Or energy is transferred from the colliding electron to the orbiting electron. So for this one, if we just go through answer by answer and just see which ones can be immediately removed. If they don't make any sense, then we can hopefully deduce the correct answer. So starting with A, the colliding electron is captured by the nucleus of the atom. Well, this kind of interaction doesn't involve the nucleus at all. It's all to do with the electron energy levels, energy shells, so we can immediately remove A. A photon is emitted when the electron rises to the higher energy level. Well, this answer doesn't obey the conservation of energy. A photon is typically emitted when an electron falls in energy level because that energy needs to go somewhere. If you think about it, the electron is losing energy by moving from a higher level to a lower level. So that energy needs to be released as a photon. So answer B is the wrong way around and is therefore incorrect. An electron is emitted when the excited electron returns to the ground state. Now this would almost be true if we replaced this word electron with photon, as we saw in option B. A photon would be emitted due to the conservation of energy, but the idea that you'd emit an extra electron out of nowhere just doesn't make sense. So C is also incorrect. Energy is transferred from the colliding electron to the orbiting electron. Well, this makes the most sense because the electron is coming in with kinetic energy. That kinetic energy needs to go somewhere, and it's actually transferred to an orbiting electron, which, as it says in the earlier part of the question, it raises it to a higher energy level. So according to the conservation of energy, D has to be correct. Light of frequency 2 × 10⁻15 Hz is incident on a metal surface. The work function of the metal is 4.6 × 10⁻⁻19 joules. Which statement is correct? Now we've got four options here. The first one being that no photoelectrons are released at all, and then others with varying values for the maximum kinetic energy on the basis that photoelectrons are released. I think what we need to do first of all is write down and use Einstein's photoelectric equation. So there's the equation. We've got the Planck constant multiplied by the frequency of that radiation is equal to the work function plus the maximum kinetic energy. So let's just substitute in our values and see what we end up with. So by multiplying the Planck constant by the frequency, we end up with an energy for these photons of 1.33 × 10⁻18 joules. As you can see, that value is higher than the work function of the metal, 4.6 × 10⁻19 joules. So there will be photoelectrons released. So we can already say that A is incorrect. Now, the quickest way to work out whether the answer is B, C, or D is to find the difference between the work function and the energy of the photons. Because as you can see from the original equation, we have to add the work function to the maximum kinetic energy to get the energy of the photons. So rearranging, we can say that the maximum kinetic energy is equal to HF minus phi, or minus the work function. So the kinetic energy of those electrons, or the maximum kinetic energy, is going to be 8.7 × 10⁻⁻19 joules. So without even having to deduce the correct answer, we know that it's going to be C. A photon of ultraviolet radiation has a frequency of 1.5 times 10 to the power of 15 Hertz. What is the momentum of the photon? Now, the equation that we need to use for this question is going to be P equals h divided by lambda. And that gives us the momentum of a photon. So let's first of all put this into a format where we can use frequency, because we know that the speed of a photon is equal to its frequency multiplied by its wavelength. So we can say that where c is equal to f lambda, 1 divided by lambda is equal to the frequency divided by the speed of light. So the momentum of the photon is equal to Planck's constant times its frequency divided by the speed of light. So let me just separate these two sets of equations so there's no confusion. So now we can substitute in our values. So we end up with 3.315 times 10 to the minus 27 kilogram meters per second, and that's going to be closest to answer C. Which statement about a couple is not true? We've got option A, it must consist of coplanar forces. B, it can produce rotational motion. C, it can produce translational motion. And D, it has a moment with units Newton meters. Now let's think first of all about what a couple means. Now a couple is a pair of forces that act away from a pivot, and they cause a rotational motion. Now we could already say that B is incorrect, because a couple is all about rotation. It causes a torque. We get a torque of a couple. If I draw a quick diagram, so I've got an example here, which is kind of a bar where forces are acting in opposite directions, and they're both at right angles to the distance along the bar to the point where they are applied. Now, those forces are actually coplanar because they're just in the plane of the paper, but rotation in its most basic form is always in one specific plane. So the forces that are causing that rotation would also have to be in that plane to cause that rotation. So they're always going to be coplanar. Technically, forces that are not coplanar could cause rotation, but that wouldn't make it a couple. You could reduce those forces down into their components in a particular plane to get the rotation in that plane, but a couple must consist of coplanar forces in order to cause rotation in a plane. C, it can produce translational motion. Well, translational motion is just motion in a particular line. It's movement along kind of x, y, z coordinates, Cartesian coordinates. That's not what a couple is about. Like we said before, it's all about rotation. So it would appear that C is the correct answer, because translational motion is not true of a couple. Just a quick note on why the answer is not going to be D. Well, the torque of a couple is equal to the size of one of the forces multiplied by the distance between them. And if we're multiplying forces by distances, then we've got a value in newtons multiplied by a value in meters. So the unit will be Newton meters. So D is incorrect. Two cars, P and Q, leave from the same point and travel in the same direction. Q leaves at time t equals 0 and P leaves 1 second later. The figure shows the velocity time graph for P and Q. What is the distance between Q and P when t is equal to 8 seconds? So 8 seconds just being the end of both lines on this graph. And we've got 4 options there, different numbers of meters. Now, the way to answer this question is to bear in mind that on a velocity time graph, the displacement is going to be the area under the graph. So if we work out the area under the graph for each of these cars and then find the difference between them, that will be the difference in displacement, and therefore the distance apart that those two cars would be. So for P, first of all, we can break the shape of the P graph down into a triangle and a rectangle. So let's work that out in meters. So we end up with 120 meters for the displacement of P. You can see I've done the area of the triangle, which is a half times 2 times 20, which is that triangle on the left here. and the area of the rectangle next to it, which is going to be a base of 5 seconds multiplied by 20 meters per second. So let's do the same for Q. So we end up with 160 meters for Q, because Q is just one big triangle, so it's a half times base times height, or half times 8 times 40. That gives us 160 meters. So let's find the difference between the two. So it's a difference of 40 meters, so the answer is going to be A. A 0.2 kilogram mass is suspended from a spring. A 0.1 kilogram mass is suspended from the 0.2 kilogram mass using a thread of negligible mass. The system is in equilibrium, and then the thread is cut. So we've got our diagram here, basically just explaining what I just read out. So we're interested in what happens to that 0.2 kilogram mass after the thread is cut. What is the upward acceleration of the 0.2 kilogram mass at the instant that the thread is cut? And then we've got 4 options here for different accelerations. Now, the thing to notice here is that initially you've got a total of 0.3 kilograms pulling down and extending that spring by a certain amount. Once you remove that 0.1 kilograms from the equation, from the situation, that 0.2 kilograms is going to bounce upwards because the force provided by the spring is going to be greater than the downward force provided by the mass. So let's work out exactly what those values are going to be. We'll do a kind of before and after system. So initially, the downward force is going to be the weight of the two masses, which is going to be equal to the mass multiplied by the gravitational field strength, which is just 9.81 newtons per kilogram. Now, initially it's in equilibrium, as it says in the question, which means that the upward force provided by the spring is going to be the same. If I just move this weight value downwards a little bit. Now we're interested in what happens afterwards when we remove the 0.1 kilogram mass at the bottom. Well, the weight is going to be lower. It's going to be 0.2 g newtons, because we've only got 0.2 kilograms this time to multiply by the gravitational field strength g. But because the spring is still extended by the same amount at that exact instant when the thread is cut, it's still going to have the same upward force of 0.3 g newtons. So what that then means is that we're going to have a non-zero resultant force acting on that mass, which is going to cause the acceleration according to, I guess, Newton's first law and Newton's second law. Newton's first law being that it will stay in the same state of motion until an external force or a non-zero resultant force is exerted. But Newton's second law saying, sort of similar to F equals ma, the resultant force on that mass is equal to its mass multiplied by its acceleration. So let's write that down. So we've got the number of newtons of resultant force is going to be 0.1 times gravitational field strength, and that's going to be the mass times acceleration. So let's rearrange F equals ma to make A the subject. So we've got 0.1 times g being the resultant force, and then 0.2 kilograms being the mass. So we end up with a half of the acceleration due to gravity, because 0.1 divided by 0.2 gives you 0.5 because it's half. So that should give us about 4.9 meters per second squared. And that's where g is equal to 9.8 meters per second squared. So the answer to this question is going to be B. A lift of mass m is suspended from a cable. The lift descends with a downward acceleration a. A frictional force F acts on the lifts. What is the tension T in the cable? And then we've got 4 options here, all involving T equals and then a combinations of M's, A's, F's and G's. Now, the trick with this question is to, first of all, draw a free body force diagram so we can see the directions of each of the forces. So we first of all have the tension in the cable, which is what we're trying to find. That's the force that's holding the lift up. We also have the weights of the lift itself. I'm not drawing these arrows to scale for now. We just want to know the direction of these forces. And we know that weight is equal to the mass times gravitational field strength. Now the other force that we need to deal with is this frictional force F which is also acting upwards because the lift is descending and the frictional force acts in the opposite direction to the movement of the lift. So we now have an upward force F, an upward force T, and a downward force W, which is going to break off into mg, which we're going to use in one of our answers. So the resultant force is going to be the difference between the two. So if we make it W minus F plus T, because we've got a downward acceleration A, so we're saying that the positive direction is going to be downwards. I've used R for the resultant force rather than F, because F obviously is already the frictional force. It's almost like the question is trying to confuse us there because they know that we're going to use F equals ma at some point. So the resultant force is also equal to the mass times the acceleration. Now, if we make T the subject of this equation, so we end up with W minus F minus ma. Now remember we said that W is equal to mg, so we can substitute that in. Now if we bring the mg and the ma together, we can actually put this into brackets. I just noticed I've used a lowercase m rather than uppercase m. This is the only mass that we're dealing with, so it doesn't really matter, but I'll put uppercase m now. So I've factorized the mg and the ma to bring the m out. So we end up with m brackets g minus a minus f. So just a note there to say that uppercase m is equal to lowercase m. It's just the notation that I use. So we end up with answer D being correct. A body of constant mass falls freely due to gravity. The rate of change of momentum of the body is equal to its, and then we've got four options here: kinetic energy, mass, gravitational potential energy, or weight. So let's go through the equations that relate to each of these terms and see if we can work out which one is equal to the rate of change of momentum. Before we do that though, it's worth just quoting Newton's second law. So the resultant force on a body is equal to its rate of change of momentum. So really, if we can find one of these values being equal to the resultant force on the body, then we're going to get the correct answer. So for option A, kinetic energy, well, straight off the bat, kinetic energy is a value in joules. And the rate of change of momentum, as we've seen in Newton's second law, is going to be presumably in newtons. But if we write down the equation anyway, you can see there that momentum could be considered to be inherent within the kinetic energy equation because we've got a product of mass and velocity, but it's velocity squared. So A would be incorrect. Option B, mass. Well, we said here that a body of constant mass falls freely due to gravity. It's got a constant mass and mass isn't changing. The point to note here again, though, is through dimensional analysis, we can say that mass is in kilograms. The rate of change of momentum has to be in newtons, so B is also incorrect. Gravitational potential energy, well, let's write that equation down. So again, obviously we can say that gravitational potential energy is measured in joules, but there's no part here that makes it equal to a rate of change of momentum. If the body is falling freely, then it's changing momentum at a constant rate. So actually where that gravitational potential energy is changing as it falls, it's getting lower and lower. If this were true and that it was equal to gravitational potential energy, then the rate of change of momentum would be constantly decreasing, but that doesn't make any sense. So C is incorrect. Option D, obviously we've deduced that it's the correct answer, but let's just explain why it is correct. We know that weight is equal to mass times gravitational field strength. Now, not only is this value in newtons, but also m and g remain constant as the body falls. You could also say, with Newton's second law, that the rate of change of momentum is also equal to the mass times the acceleration. So force is equal to mass times acceleration, but also equal to mass times the rate of change of velocity, which is the acceleration. But then that's also equal to the rate of change of momentum. So if we backtrack towards F, we can actually say that W, being the only force acting on the body, is the resultant force. So all of these values are equal. So the weight is equal to the rate of change of momentum if you look at either ends of that chain of equations. So D is correct. An electric vehicle is driven by a motor which produces a constant driving force. The vehicle travels from rest along a straight horizontal road. Friction and air resistance are negligible. Which statement describes the variation with time of the power developed by the motor? Now, the first thing to note here is where it's traveling from rest and it's being supplied a constant driving force, this vehicle is going to be accelerating. We've got negligible friction and air resistance. So the only force acting on that vehicle is going to be the force provided by the motor. So let's write down an equation for the work done on the vehicle. So work done is equal to force times distance. If we divide both sides of that equation by time, we can see that work done divided by time is equal to force times distance divided by time. Work done divided by time is just power. And then if we separate the force and the distance divided by time, we can say that it's actually the force times the speed. Or in terms of vector quantities, it's force times velocity. Now, we're supplying power to the vehicle. It's providing a constant driving force, but the velocity is gradually increasing. Now, as we said at the beginning, it's going to be accelerating. There's a constant force, which means that there's a constant acceleration. So if the velocity is increasing linearly from zero because it's a constant acceleration, then with a constant force, then that means the power has to be increasing linearly from zero as well. So the answer to this question would need to be B. Which is a correct statement about mechanical power? We've got four statements here, some of which are more obviously wrong than others, but let's go through which ones those are. So option A is a vector quantity. Well, we know that power isn't a vector quantity. It's calculated as being energy transferred or work done divided by time. Energy and time are both scalar quantities, so A is incorrect. It's measured in joules. Well, as we just said, we calculate power by dividing energy by time, or work done divided by time, so it should in theory be in joules per second, not joules. We know that power is actually measured in watts, so B is incorrect. In fundamental units, its unit is kilogram meter squared per second cubed. We're going to come back to that one because we need to actually look at the equation in more detail and break it down into SI base units. We'll do that in a second. Option D, it can be calculated from force times distance moved. Well, actually, that's how to calculate work done. We're actually going to use that in working out option C. So D is also incorrect. So let's just prove that C is definitely correct. First of all, power is equal to work done divided by time. So we can say that 1 watt is equal to 1 joule per second. The next thing that we can say is work done is equal to force times distance moved. So actually work, instead of being in joules, we can say is in Newton meters. The next thing that we can say is a Newton can be written as a kilogram meter per second squared because force equals mass times acceleration. So we can multiply kilograms by meters per second squared to get newtons. So what we actually got there is a watt is the same as a kilogram meter per second squared per second, which is 1 kilogram meter per second cubed. So actually C is correct. A load of 50 newtons is suspended from a wire that has an area of cross-section of 1 millimeter squared. The stress in the wire in pascals is between, and then we've got 4 answers here, 4 different ranges. So what we need to do is first of all write down the equation that we can use to find stress in the wire. So sigma represents the stress. Now, it would seem that we would just divide the force of 50 newtons by 1 millimeter squared, but remember that we need to convert the 1 millimeter squared into SI units. Now, 1 millimeter squared is actually equal to a millionth of a meter squared. Because if you picture a grid, a square grid that's a meter long and a meter tall, there are 1,000 millimeters in a meter, So if you break this grid down further, in columns of width a millimeter, there will be 1,000 of those columns, and then if you do the same the other way, in rows of height 1 millimeter, there would be 1,000 that way. So over the entire meter squared, if you counted up all of the millimeter squared squares, then there would be 1,000,000 of them. So a millimeter squared is a millionth of a meter squared. Now, if we divide the 50 newtons by 10 to the minus 6, we end up with 5 times 10 to the power of 7. And that value is between 10 to the 6 and 10 to the 9. So the answer is C. Which combination of properties would produce the smallest extension of a wire when the same tensile force is applied to the wire? And we've got a table here with different multiples of cross-sectional area, length, and Young modulus. What we need to do first of all is write down the equation that ties all of these together. So first of all, I've written that Young modulus E is equal to stress divided by strain, so stress being that sigma and strain being that epsilon. Now we need to write down what stress is in terms of other values and what strain is in terms of other values. So I've written here that the stress is equal to the force divided by the cross-sectional area, and the strain is equal to the extension divided by the original length. So what I've then done is I've put all of those into the equation so that we can say that Young modulus is equal to force times original length divided by cross-sectional area times extension. What we can then do is change some of the values around. For example, cross-sectional area in the table was represented by an X rather than an A. Now that might lead to some confusion because we've got an uppercase X and a lowercase x, but what we need to do is rearrange the equation to make lowercase x the subject because we're looking at the extension of the wire in terms of all of those other values. Now what we're interested in is what those changes in these three different values will do to the value of x. So I'm going to write down next to the option selection boxes how the expression changes and what the multipliers come out as in terms of that original value of x. So I've just changed the lowercase L's to capital L's because that's what the original length is in terms of. You'll notice for the first one, the extension with YA, we're multiplying L by 3 this time. So if we bring that 3 out of the equation, then the overall extension is going to be multiplied by 3. For the second one, we've got FL over 2x times E, because this time the cross-sectional area is multiplied by 2. So overall, that would halve the extension. So already B has a lower extension than A. So actually, we can say that A would be incorrect because it's not the smallest extension. For option C, you can see that L is multiplied by 3, but then E is also multiplied by 4. But because 4 is on the lower part, it's in the denominator of the fraction, then we're dividing by 4. So XC will be multiplied by 3/4, 3 divided by 4. And then finally, you can see that we're multiplying the cross-sectional area by 2, we're multiplying the Young modulus by 4. So for option D, we're dividing everything by 8 because the 2 and the 4 are both in the denominator. So the extension is divided by 8. So actually, D would give the lowest extension. A rubber belt in an electrostatic machine has a width of 0.1 meters and moves with speed 0.4 meters per second. Each square meter of the belt carries a charge Q coulombs. The charge is removed and transferred to a metal sphere. Then we've got the metal sphere here with the rubber belt that's connected to it, and we're interested in how much charge is moving every second. You can see the question there. It says, what is the charge collected by the sphere each second? And then there are 4 options there, and they're each in terms of Q. So let's go back to the first part of the question. You'll notice here that it says each square meter of the belt carries a charge of Q coulombs. Now we want to know how much area of belt passes through every second, because then we can make that a proportion of that value of Q. Now, in order to work out the amount of area that moves through per second, we want to multiply the length that moves through per second by the width. So imagine this rectangle here as a piece of that belt. It's got 0.1 meters of width and 0.4 meters in length. Obviously, that's not to scale, as you can see, but that is the size of the piece of belt that moves every second. Now, we're interested in the amount of charge that moves per second. So let's first of all multiply these two lengths together to get the area of belt. So we've got 0.04 meters squared of belt that are moving every second. Now, if 1 square meter of the belt carries a charge of Q coulombs, then instead of saying meter squared, the amount of charge that we're going to get is going to be in terms of Q. So what we could do is we could make both of these in terms of seconds and say per second, but we don't really need that. If we look down at the options for this question, you can see there that option B is 0.04 Q. That is the amount of charge collected by the sphere, i.e. the amount of charge that passes along via the belt every second. So the answer is B. Charged plates X and Y have a potential difference of 1.5 volts between them. We've got a diagram there of plate X and plate Y, plate X being 0 volts and plate Y being plus 1.5 volts. Which particle gains 3.0 electron volts of kinetic energy when moving from Y to X? And then we've got 4 particles here, proton, positron, electron, and alpha particle. Now, before we go any further, let's just write down what the definition of an electron volt is. 1 electron volt is the energy gained by an electron when it is accelerated by a potential difference of 1 volt. Now, for that electron, the thing that's causing it to be accelerated is its charge. Now, it has a charge of 1.6 times 10 to the power of minus 19 coulombs. We don't actually need this for this question, but what we do need is the relation between energy and voltage. So an electron volt is actually the charge on an electron multiplied by the potential difference of 1 volt. So if we can identify the charge that this particle has, then we can identify which one it is. So let's rearrange the equation first of all. The charge is equal to energy divided by potential difference. We'll stick with electron volts and volts because we'll end up with a value that's just a multiple of E, or the multiple of the charge on an electron. So if we divide 3 by 1.5, so we end up with a charge of 2 times the charge on an electron. So we know that it's definitely not going to be C because C is just going to have a charge of E. And actually, A and B, a proton and a positron, both have the same charge, regardless of whether it's positive or negative. The magnitude of that charge is going to be the same. It's definitely not going to be 2 times the charge on an electron. So the answer is actually an alpha particle, and the reason for that is that an alpha particle contains 2 protons and 2 neutrons. And the fact that it has 2 protons means it has double the charge of an electron, because a proton has the same magnitude of charge of an electron. It's just reversed in terms of the plus and minus. So the answer is going to be D. The diagram shows part of a circuit and the currents in the circuit. So we've got some currents here, some resistances, or some fixed resistors, and then you've got the earth, which is that set of 3 lines at the bottom. What is the potential difference between point P and earth? And then we've got 4 values of voltage there that we need to choose from. So looking at the diagram, the first thing to do is to use the equation V equals IR to find the potential difference across that 10 ohm resistor. So we can multiply the 2 by the 10. So we end up with a potential difference of 20 volts. Now, the next thing to do is to work out how much current is flowing through that 20 ohm resistor so that we can work out the potential difference across that resistor as well. Now, this is where Kirchhoff's first law comes in. The sum of currents entering a junction is equal to the sum of currents leaving the junction. And you can see that with this junction here, there are 2 amps coming in from the top and 4 amps coming in from the left. So leaving the junction through that lower down route, there must be 6 amps. So using the same equation that we used before to find the potential difference across the 20 ohm resistor, we end up with 120 volts. So in total, with these 2 resistors combined, remember we add the potential differences in the same way that we would add the resistances, we end up with 140 volts. So let's look at our options. You can see there that option D has 140 volts, so that is our correct answer there. A voltmeter has a resistance of 4 kilo ohms and reads 1 volt for every scale division on the meter. A power supply of EMF 20 volts and negligible internal resistance is connected across this voltmeter and a resistor in series. The voltmeter reads 2 divisions. Now, the first thing that I would say, it seems like this question is trying to confuse you a little bit. 2 divisions basically just means 2 volts. You can see that it's mentioned in the question earlier on. So the voltmeter is reading 2 volts. What is the value of the resistor? Now, for this, I would draw a diagram just so that we can see exactly what's going on. It's very difficult to picture when you're just going off a description from the question. So there's our power supply of EMF 20 volts, and it's connected across the voltmeter and a resistor in series. I've not included an internal resistance because it's described as negligible. So what we can do is apply Kirchhoff's second law here. Obviously, that's heavily abbreviated, but the sum of the EMFs in a closed loop is going to be equal to the sum of the PDs in a closed loop, EMF being electromotive force and PD being potential difference. So actually, the value of the resistor we can calculate using the voltages in this loop. The voltmeter reading is going to be the difference between the EMF of the cell and the potential difference across the resistor. So let's start writing down some values. So we've got 20 volts for our cell. We've got 2 volts for our voltmeter. So already we can tell that where the resistor is going to be the difference between the two. So the potential difference across the resistor will be 18 volts. Now, what's interesting about this is that the resistances actually fall into the same ratio as the voltages. So the ratio of the potential difference across the voltmeter to the potential difference across the resistor is the same as the ratio of the resistance of the voltmeter compared to the resistance of the resistor, because it's all to do with the amount of energy that it's taking out of the circuit. So they're at a 2 to 18 ratio. We know that we've got 4 kilo ohms on the voltmeter. Now what we can do here is where we know that the potential difference across the resistor is going to be 9 times the potential difference across the voltmeter, because it's how many times you can fit 2 into 18. We know that actually if we multiply the 4 kilo ohms by 9, we will get the resistance of the resistor. So we end up with a resistance of the resistor of 36 kilo ohms. So that's going to be option B. 2 cylindrical wires P and Q are of equal length and made of the same material. The diameter of P is greater than that of Q. P and Q are connected in series, and the ends of this arrangement are connected to a power supply. And we've got a diagram there of P and Q. You can see that P has got the higher cross-sectional area. Which 2 quantities are the same for P and Q? Now, the first thing that we need to point out is that these 2 conductors, if you like, are made of the same material. Now, if they're made of the same material, they will have the same resistivity. Remember, resistivity varies with conducting material. So what we can already say is that resistivity remains the same. Let's look at another one of these physical values in this table. If we take a look at current, well, we know that they are connected in series. So the current through them needs to remain the same according to Kirchhoff's first law, which is that the current flowing into any point is equal to the current flowing out of it. Because there are no junctions, no branches here, there is no variation in current, so current remains the same. Well, from this we can already see that B is going to be correct, but let's just look at the other values and explain why those are incorrect. So potential difference across the wire. Well, for this, let's take a look at the resistivity equation. Well, ignoring potential difference for a second, what we can say is that where the cross-sectional area is varying between P and Q, while keeping the other values the same. Remember, they're of equal length. So we're keeping resistivity and length constant. If we're varying the cross-sectional area, we're also going to vary the resistance. So resistance is not going to remain the same for P and Q. So moving back to potential difference, if the current flowing through them is going to be the same, but the resistance is going to be different, that means that the voltage has also got to change. We just write down the equation that links those together. So V equals IR, potential difference is equal to current multiplied by resistance. So if we're changing the resistance while keeping the current the same, then we're going to change the potential difference as well. So actually, potential difference is going to change. So from this table, what we can see is that the only option where both values are staying the same is going to be for option B, because resistivity and current are constant. In the circuit below, the initial voltmeter reading is 0. And we've got a diagram there with 4 resistances P, Q, R, and T. The temperature of the negative temperature coefficient thermistor is then increased. Which change to the circuit could restore the voltmeter reading to 0? And we've got a set of changes there to R, P, and Q as the options. And the first thing to say for the negative temperature coefficient thermistor is that when you increase the temperature, you actually decrease the resistance. So that will come in useful shortly. Now, for this kind of circuit is what we call a Wheatstone bridge. And in that type of circuit, the ratio of the top resistances is equal to the ratio of the bottom resistances. So if we just put that into equation form. So what we're doing by decreasing the resistance of thermistor T is we're increasing the value of the denominator on the right-hand side fraction. Now, in order to restore that fraction back again so that it keeps the same as the ratio of the resistances P and Q, what we need to do is decrease the value of R, decrease the resistance of R, because if we make the denominator smaller, we need to make the numerator smaller as well to keep the fraction the same. So the answer to this question is going to be A. An electric motor lifts a load of weight W through a vertical height h in time t. The potential difference across the motor is V and the current through it is I. What is the efficiency of the motor? Now for this question, the first thing to do is write down what we mean by efficiency in equation form. So efficiency is equal to useful energy output divided by total energy input. Now for useful energy output, it said that the electric motor is lifting a load of weight W through a vertical height h in time t. So the useful energy output is actually the movement of the motor. Now, if it's lifting an object, it's increasing that object's gravitational potential energy. So let's write down that first of all. So that's our equation for change in gravitational potential energy is equal to the mass times the gravitational field strength times the change in height. Now, interestingly, we can change that to W times H because weight is equal to mass times gravitational field strength. So we can make a substitution there. Now, instead of delta H in the question, it's just saying H. So let's change that as well, remove the delta. So our useful energy output is going to be W times H. So now we just need to work out what we're going to divide it by putting in the total energy inputs. Now the energy is being input to this motor electrically, so we're interested in the electrical power of that motor, which is equal to V times I. I won't label this one here because there isn't an awful lot of space and it is mentioned in the question, but power is equal to potential difference multiplied by current. If we combine that with power is equal to energy divided by time, because power is the rate of change of energy or the rate of energy supply, we can say that the energy is equal to potential difference times current times time, because we're saying up here that energy is equal to power times time. So we now have our bottom half of the fraction for the total energy input. So the total equation for efficiency is equal to weight times change in height divided by potential difference times current times time. So the answer to this question is going to be C. An object of mass m moves in a circle of radius r. It completes n revolutions every second. What is the kinetic energy of the object? The first thing that we want to do is write down the equation for kinetic energy, because that's going to relate the mass and the speed. So kinetic energy is equal to 1/2 times the mass times the speed squared. Now, we're fine with the mass because it gives us that in the question. What you'll notice there is it's talking about a radius r and the number of revolutions per second, n. So let's think of n as being like a frequency. And what we can then do is relate that frequency to the angular frequency by a factor of 2 pi. And that is the number of radians that mass moves through every second. Now we can relate the angular frequency to the linear speed. V is equal to omega r, so the linear speed is equal to the angular frequency multiplied by the radius. Now I won't put any labels on that because V we've already labelled as speed, omega is angular frequency, which you can see in the middle, and r is radius, which is mentioned in the question. So what that tells us is that n is equal to V divided by 2 pi r, and that's how we connect to kinetic energy because we've got that value of V. So if we first of all say by rearranging that V is equal to 2 pi r n, what we can do is make a substitution and we can put that substituted value of V into the kinetic energy equation. Now if we expand those brackets out and then cancel the 4 with the 1/2 to make 2, you'll notice that I've written these symbols in a very specific order for a reason, and that is that it's the same as option C, which is 2m pi squared n squared r squared. So that's going to be our correct answer. The graph shows the variation of displacement d with time t for a particle moving with simple harmonic motion of period t. We've got a graph there, you can see it's a sine wave, and it only goes up to that time period of t, and it's got displacement on the y-axis and time on the x-axis. Which graph shows the variation of kinetic energy, Ek, of the particle with time? Now we have 4 graphs here, and then we've got A, B, C, or D, which link up to those. Now the first thing to say, straight off the bat, is that kinetic energy cannot be a negative value, so the answer cannot be A or B. You'll notice both of those graphs have negative regions. So we're looking at either C or D here. So let's go back to the graph. An important thing to note about a graph such as this, a displacement time graph, is that the areas where the graph is steepest are going to be where the particle has the highest speed. Now, I specifically said speed there as a scalar quantity rather than velocity, because that can have high positives and negatives and so on. But actually, kinetic energy only relies on the scalar quantity of speed. So the steepest points will be these 3 points here, and that is where the particle has the maximum speed. So in theory, on a graph of kinetic energy against time, that is where the particle should have the highest points. But let's also look at where the graph levels off. Those are the points where the gradient is going to be 0. So the gradient of the graph is going to be the velocity. If that's 0, then the velocity is 0, the speed is also 0. So those are the points where the kinetic energy should be 0 on its own graph. So we just add in some labels. So 2 example points there. So we're looking for a graph where it starts off very high, and then at about a quarter of the time period in, it should be 0. So as you can see from these graphs, the only one that does that is going to be option D. You can see the graph starts out high, and then a quarter of the time period in, it's down to 0. So it's doing the opposite of option C. So the answer here is going to be D. Two pendulums, A and B, oscillate with simple harmonic motion. The time period of A is 2 seconds, and the time period of B is 1.98 seconds. A and B are released in phase. What is the number of oscillations of A before A and B are next in phase? And we've got four options here. We've got 49, 50, 99, or 100. Now, the thing to do here is to picture what's happening between those two pendulums as time goes on. The way I would do this is start by drawing a table and fill in the values for the difference in phase each time there's a swing. So we've got a table here that tells us the number of swings that B has done, which for a while is going to be the same as the number of swings that A has done. But we've also got a column that tells us how far ahead B is in seconds. So we know that after one full swing, B is going to be 0.02 seconds ahead, because that's the difference between the two time periods. And then after two swings, it's going to be 0.04 seconds ahead, and so on. So you can see there, by taking values on the left column and multiplying them by 0.02, you get values on the right column. So we're interested in the number of swings that B has done when it's 2 seconds ahead, or i.e. when it's a full phase of A ahead, i.e. they're back in phase. Now this should occur when B has done 100 swings. So we know that the answer is definitely not going to be A or B. Now we just need to double check whether it is 100 or whether it is 99. You'll notice the question says, what is the number of oscillations of A before A and B are next in phase? So actually B has completed 100 swings, but remember it's 2 seconds ahead of A, which means it's a full swing ahead of A. So actually A has only done 99 swings, and that's what the question is asking for. So be very careful there. The correct answer is actually C. Very easy to slip up on this one. The frequency of oscillation of a vertical spring is F when the mass hanging from the spring is M. What is the relationship between F and M? The first thing that we need to do is write down the equation for the angular frequency of a mass spring system. So the angular frequency omega is equal to the square root of the spring constant divided by the mass. Now instead of angular frequency, let's use the normal frequency F. So we're getting closer there to that relationship between F and M. You'll notice it's still locked within that square root with the k. So if we rewrite the square root of k over m as the square root of k divided by the square root of m. So where the spring constant is a constant, we can see there that the frequency is going to be proportional to 1 divided by the square root of m. Or in other words, frequency is proportional to m to the power of minus a half. Because 1 divided by something is that thing to the power of minus 1, and the square root of something is that thing to the power of a half. So the answer to this is going to be A. A metal panel is driven to vibrate at different frequencies. The amplitude A of the vibration is measured at each frequency. The graph shows the variation of amplitude with driven frequency. And we've got a graph here. You can see there's a point of resonance where the peak is at 100 Hertz, and that's also got an amplitude of 1 millimeter. The damping of the metal panel is increased without changing the mass of the panel. Which graph on the opposite page shows the variation of A with frequency with increased damping? Now, before we look at those graphs, there are three things that happen when you increase the amount of damping in a resonance system. And those are: the resonance peak occurs at a lower amplitude. You can see here that it's at 1 millimeter. It's going to be less than that when resonance occurs. So we're looking for a shorter peak. Resonance peak is more spread out horizontally, so it won't be such a tall, thin peak. It will spread out in terms of frequency. The peak occurs at a slightly lower frequency, so what we should observe on this graph is that it's going to peak at slightly less than 100 Hertz. It will be slightly to the left. So looking at our graphs, we can see that the only graph that meets all three of these criteria is going to be D, because you can see with option D that not only is the peak lower, more spread out, but it is also slightly to the left of 100 Hertz, so it's at a slightly lower frequency. So the answer here is going to be D.